Hello, good morning, Harish sir.
Yeah, good morning, ma'am.
How are you, sir?
I'm fine.
Okay, sir.
So it's
So,
weekend.
yeah,
Yeah,
सर कैसा लग रहा है आपको सर ये बताइए.
I'm fine. Yeah.
Okay. Uh, टाइम दें पार्टिसिपेंट्स को अभी.
Yes, please. Yes, yeah.
ओके, ठीक है सर, फिर 5 मिनट और दे देते हैं,
Yeah,
कनेक्ट
please.
होने देते हैं. ओके.
Good morning, all of you. On the behalf of Information Technology Department of JCRC, I welcome you all on fifth day of Faculty Development Program on Quantum Computing. Our keynote speaker is Dr. Hees Sahu. He is a scientist at DRDO Delhi. Today, sir will give us information about quantum cryptography. I request you, sir, to kindly start the session.
Thank you, ma'am. So, good morning, everyone. So, am I audible and visible to you?
Yes, sir.
And my slides are visible? The screen is visible?
Yes, sir.
Okay. So, today we will be covering this quantum self cryptography. So, in the last 2 days, we have seen this Shor's and Grover's algorithm, and a little bit we have seen what the effect of this quantum algorithm on our classical cryptography. So, in the classical cryptography, if you see, there are symmetric key cryptography. Okay, so where the same key is used for encryption and decryption. So in that case, we have seen this DES and AES kind of ciphers, where same key is used for encryption and decryption. And we have also seen the effect of Grover's algorithm on exhaustive trial attack of using Grover's. So what was the idea there? That this key was there. Let's suppose this key is, so this key was there, and there will be, let's suppose if it is DES, then there will be this many keys. Possible keys are there. So to find the key, what we were doing there is we are applying this Grover search. And if we do the Grover search, so this can be done in 2 to power 28. So basically square root of 2 to power 66. So if we do this trial or this exhaustive trial attack on classical computer, then what we require is we require these many trials. So whatever the key space or the possible number of keys, we have to try exhaustively one by one. So if we do that thing on classical computer, then 2 to power 56 keys on an average you have to try. But if we use quantum computer and this Grover algorithm to try the keys exhaustively and find the correct key, so then this space reduces to 2 to power 28. So if we are having this kind of key, then effective key size is basically 28 only. So half the key we are getting the strength. If we are having this Grovers and quantum computer with us, then the symmetric key strength is reduced by half. So whatever the key size is there, let's suppose key size is 56 in DES, then the effective key size after using this Grover search, it becomes 2 to power 28. And that is perfectly doable on a classical computer. This exhaustive trial 2 to power 28 is less than 1 billion or so. So these kind of trial we can do. But if you see this 2 to power 56, then it is a very large space and difficult to try on classical supercomputer also. So in the symmetric key cryptography, we have seen this using these Grovers, we can attack and find the key exhaustively, efficiently. So there are these kind of stronger algorithms are there, namely this DES that is no longer used because the key size is small. Only 56-bit key was there. So nowadays this triple DES. So triple DES key size is 56 into 3. Here if you see AES, then it is comes in 128, 192, 256 bit variant. Here again it is 128. So currently if you see, there are ciphers which are having key bit length of 128. So if we are having this much key size, 128 bit, then the possible number of keys will be 2 to power 128. So using Grover, if we do, then it becomes 2 to power 64. And this 2 to power 64 is doable on supercomputers. So this Grover is posing a threat, but what we do to overcome this threat, if we increase the key size, let's suppose we are using this AES 256. So where the key size is 256. So what will be the key size, key space? It will be 2 to power 256. But if we use the Grover, then what it will become? Can anyone tell? This AES 256 is having this 256-bit key. Okay. So total space will be, so it will be 2 to power 128. So using this Grover on a quantum computer, we can reduce that space to 2 to power 128. But this 2 to power 128, we have to perform on classical computer. And that is not doable on classical computer as of now. Or maybe next 100 year also, we will not able to do this thing, 2 to power 128. Because 2 to power 128 is a very large space. So if we try that thing exhaustively, then we cannot do it in our lifetime on a fastest supercomputer of classical computers. So the thing is that if the key size is 128, then we are kind of unsafe because Grover can reduce that space in 2 to power 64 and that is doable. So what we can do is, instead of using this 128-bit key size, we should move to 256 kind of bit size keys. So if we are using AES 256, then we are okay. So wherever this key size is less than this 256, then there is a threat by Grover. So the way to overcome those kind of attack is just double the key size. So what is the idea? Threat was there from Grover, and to overcome that, have double the key size. Okay, so doubling the key size will keep us safe in case of symmetric key cryptography. Okay. So like this is AES 128 cipher I have shown here. So Grover can reduce the complexity of exhaustive trial in this kind of cipher. So we should move to 256. So there is another one kind of, yeah. So we have seen this. These are the algorithms for symmetric key cryptography. Okay, and there is a one basic and very safe kind of cipher that is called one-time paid cipher. So what is the idea there is, whatever message is there, okay, some message is there. So what you do is you choose a random. So what is this one-time paid? It is a random bit string. Call it as key also. So whatever your plaintext message is, you are having same size of paid, and that is completely random. So what you simply do is you do XOR this plaintext with that key or one-time paid. So once you XOR this paid, you will get the ciphertext. Since this is random, so this will also be random. So this ciphertext is completely random. So we don't have any information. If you don't know this paid, then we cannot take out plaintext from this. So taking plaintext from it, not possible without knowing the key, without knowing this paid. So what is the idea is that this paid, if we know, then we can simply XOR it, then we can get the plaintext. So yesterday I also tell you guys that this XOR is this XOR get us this property, nice property. So some P is there, and if you are XORing it with K 2 times, so one time you are XORing, you are getting C. If you XOR it again, P XOR again with the same key, then this effect of this key will be cancel out. So we will get the original P. So the idea is that when you XOR the plaintext 2 times with the key, then you will get the P only. See here. So this X is our the X bit string is our plaintext. This is our key. So what is the property of this key? It is completely random. Okay. And then we are getting ciphertext. So what will be our ciphertext? Bitwise XOR of this plaintext and key. So we get this. So this is our ciphertext Y. Okay. And to get this X again, what we have to do is, what we will do? We will XOR this Y with again this K. Okay. And this Y was nothing but X XOR K. X XOR K. So 2 times XOR with K will nullify its effects, and we will get the original X. So this kind of cipher is shown to be providing perfect secrecy. Means if we use this key as a completely random key and one time only. So next time if we get some different X, then we are not going to use the same key. We will be having a different completely random key next time. So if we have this key to be used only one time and it's completely random, then we are perfectly secure. Nothing, not any kind of attack is possible on this kind of cipher. So they provide perfect secrecy, but the issue is that this key should be completely random. Okay. So the challenge is to get a completely random key each time for each messages, and this one-time paid of this key should never be reused. Okay, so it should not be reused. So these two things are required. It should be completely random, and as long as the plaintext, and secondly, you cannot reuse it. So every time you have to have a different key to encrypt different messages. Okay, and it should be having length equal to the message at least. So the thing is, the challenge here is, what is the challenge? Let's suppose if I want to send a 1 GB file using this one-time paid. So what should be the size of my key? Can anyone tell? If this plaintext message is of 1 GB, then what should be the key size of this key? Anyone?
1 GB.
So I should 1 GB only. So whatever the plaintext size, I should have the same size of key at least, and that too completely random. Okay. So this key, let's suppose these two party are there, A and B. So they both should have this K. Okay. Then this A can let's suppose some P was there, 1 GB P was there. So simply it will XOR P XOR, it will send here, that is C. Okay. So if this C is going to the public channel, So adversary can this C, can see this C, but adversary does not have this K. Okay, so this only the party B on receiving this C, what it will do is it will just XOR this C with K, so it will get the P. But the problem is that how we will have this kind of 1 GB of key, 1 GB key for one file. So, and again, if I want to send something more information, then next time I cannot use this 1 GB key. I should have another key that should not be repeating. So these two things are challenges. We should have a completely random key and we should have a different key each time. So because we cannot reuse this key next time, so these requirements are very challenging to distribute this kind of key, large keys between these two parties. So what the requirement is that this key should be between both A and B should have this key. So how to distribute this key is called the key distribution challenge. What is key distribution challenge? That how to distribute these kind of random long keys to these parties A and B, because this A can be in India, this B can be in America. So what will happen? These two parties should have the same key. So how you distribute this key prior to doing this encryption? So that is a challenge. How it is handled, that we will see. So time being, this two things are there. OTPs should be random and should not be reused. So what if we reuse it? Let's see. So what we are saying is that ideally we should not reuse it. But let's suppose if we are having this message. First message, this is our M1 and this is our K. Okay. Here again we are using this K and this is our M2. Okay. So this is our first message M1 which we want to send. So we use this key K. So what we will get? This is completely random. So this cipher will be also completely random. So this C1 we will get. Okay. Let's suppose this is another message M2 and using the same key. So ideally this OTP suggests that we should not reuse it. But suppose we reuse this K here. Okay. For different message M2. Then we will get also a completely random thing. So these things are not equal. They are not equal. Okay. So this C1 and C2 are not equal. Okay. But what the common thing is they are having this XOR with K kind of thing. Okay. So this is C1 and this is C2. So what can we do if we XOR this C1 and C2? So this C1 and C2 will travel on a public channel. So adversary can have access to this C1 and C2. But until and unless adversary does not have this K, he cannot derive this M1 and M2. But what we did is we used the same key for both M1 and M2. Let's suppose adversary has this both C1 and C2. So what adversary is doing is, if adversary know this thing that they are this sender is using the same key, so what he will do is he will XOR this C1 and C2. Okay. Now you see, put the value of C1 and C2. So what? So what adversary is doing is he is computing this C1 XOR C2, which is on public channel. He can see it and use it. So if we put the value of C1 and C2, what was C1? M1 XOR K. What was C2? That was M2 XOR K. And as I have already told, that if we do XOR with same thing 2 times, then its effect is nullified. So what will happen with this K and K 2 times XOR? Can anyone tell? If we are XORing with same thing 2 times, then effect of that thing will be cancel out. So this K XOR K is nothing but 0. Yeah. So K XOR K is basically 0. And if you do XOR with something with XOR with 0, then the thing will remain same. So this K XOR K is basically 0. And if you are XORing with 0, then it will not have any effect on the X. So what it will get is, it will get M1 XOR F2. Although this adversary is not having M1 and M2, but it is having an XOR of those two messages. So this M1 and M1 XOR M2 is leaking some information about message M1 and M2. Not completely about M1 and M2, but XOR of them is with adversary. or Eve. Okay. So if you see this M1 XOR M2, so if you do XOR this M1 and M2, so you will get this kind of thing. But here you can see you are having some information leaked to the adversary or the Eve. So seeing this M1 XOR M2, so see this is our M1 XOR M2. So adversary can have a partial information about our messages if we use the key 2 times for as a paid. So it is not advisable to reuse this key K. So what is the idea for perfect secrecy in OTP is every time you should have a different key. So if you have a different key K1 and K2 2 times, so then this thing will be completely random. But adversary, if we do X1 XOR of C1 and C2, then this K1 and K2 will not nullify and they will remain. And since this K1 and K2 are completely random, so you can see it is, let's suppose this K1 XOR K2 is some K3. So if you XOR with some completely random thing, so this K1 and K2 are completely random. So let's suppose their effect is K3 and that is also completely random. Then if you XOR this M1 XOR M2 with K3, a completely random thing, okay, then you will get completely random thing. So you cannot make out any information out of this. So the idea is if you use the paid 2 times for different messages, then there is a chance that you will leak some information about your message M1 and M2. So what is the idea? That you should have this key use only 1 time and discard it. So next time you will make sure that it is not reused. If you reuse, then it is a problem. Okay. So what are the challenges about this symmetric key cryptography or OTP also? That a sender and receiver should have already a secret key between them. Okay. So distributing this secret key to sender and receiver is the challenge, and that is called key distribution problem. Okay. So this how to distribute this key between these two party, and in case of OTP we require larger keys. So how to distribute them? That is a challenge. But yeah, so these things are challenges in our asymmetric key cryptography, and we have also seen the effect of this Grover on symmetric key cryptography. So if we are having this Grover, then we should just overcome that. What we should double the key size. So doubling the key size will nullify or overcome the effect of Grover search. So this Grover's is having threat to the symmetric key, but it can be overcome by just simply the doubling the key. But what about this key distribution? That we will see. So before going to this key distribution challenge that we will see, and it is solved by quantum key distribution. We will see using this quantum key distribution, we will solve this problem securely. So before moving to that, just briefly go to that asymmetric key cryptography. So symmetric we have seen this Grover was the threat, and using this doubling the key size, we can overcome that effect. So in the asymmetric key cryptography, a user has 2 kinds of keys. One is a public key and one is a private key. Okay. So the sender, if this is our Alice and this is our Bob B. So if sender A want to send some plain text message to Bob, then what this Alice should do? Alice will simply take the public key of this B. So these are public key of B. Okay. So if A want to send a message to B, then he will use the public key of B to encrypt. So it will be a cipher text. So it will go on a public channel. But corresponding private key is with Bob only. So Bob only can decrypt this cipher text. So the idea is in asymmetric, we are having 2 pairs of keys for each user. So public key is used for encryption, and only the recipient, which is having the private key, can decrypt it. So this kind of system are there, and popular systems are RSA, ECC. So RSA we have seen a day before yesterday. ECC, Diffie-Hellman, Al-Gamal, DSA. These kind of public key ciphers are widely used over internet, over your banking systems, over your e-commerce. So these systems are in place. So yesterday, day before yesterday, we have seen this. It is being used on online SBI or other things. So what was the threat there for this kind of cipher which we have seen? For asymmetric RSA kind of algorithm, we have shown some algorithm that was a threat. What was that? Can anyone tell? This RSA is based on underlying hard problem, that is integer factorization. Okay, so this integer factorization is difficult for classical computer, but for quantum computer, which algorithm can factor this efficiently in polynomial time?
Shor's algorithm.
Sure.
Perfect. Thank you. So using this Shor's, we can factor it. So if there are large number also, then we can do it in polynomial time on quantum computer. So there is other algorithm called elective car cryptography. So they are based on some other problems. So they are generally based on this discrete log problem. Okay, and that also can be converted into period finding problem. Okay, and this period finding using quantum Fourier transformation and source algorithm can be done in polynomial time. This other cipher are mostly based on discrete log problems. Okay, so this is also hard problem for classical computer to find the discrete log, but that discrete log can be converted into period finding. Okay, and as we have seen before yesterday, that period finding kind of problem can be done using quantum Fourier transformation and source algorithm in polynomial time. So those systems are having threat. Okay, using quantum algorithms such as Shor's. So these all systems are having threat from Shor's algorithm or its variant. Okay, Shor's and its variant. So, okay, so this algorithm yesterday we have seen, day before yesterday, RSA algorithm, how it used, and so underlying, if we are able to factor this n, given this n, if we can factor this, then we can break this cipher, and that is widely used. So keep this thing in mind. So whatever mostly public key cipher which we are currently using are having direct threat from this Shor's algorithm. Okay, but the challenging thing is that if we are using 2048 require 2 times of this 2048 plus 2, so almost 4000 qubits. 4000 qubits we require to factor this kind of number. But the current challenge is that current quantum computers are having only hundreds of qubits. Currently, what is the challenge? Whatever quantum computer we are having only qubits in hundreds of order. So they are, if once we have this kind of 4000 or 5000 qubits, then we can break this kind of cipher. So there is a direct threat. And how we can overcome? By doubling this size will not solve the problem. So doubling the size will just increase the time little bit for the source algorithm. Let's suppose if you are able to this thing problem in 5 minutes, then if you increase the size, double it, then maybe in the 10 minutes we can do it. So because it is polynomial, so doubling the size will not solve the problem here. But in case of Grover's in symmetric key, doubling the key is solving the problem, because the complexity was like this. 2 to power n was there in classical, and it is 2 to power n by 2. So symmetric if we talk, so classically if you use Grover, then this will be 2 to power n by 2. So what was the idea there? That it was exponential, still it is exponential after Grover also. That will be just square root of that thing, na? But here classically this problem was exponential, but using the Shor's it is polynomial. So doubling the this bit size will not solve the problem in this kind of asymmetric scenario. So we should replace these systems. How we should what those system we call? We call those systems are quantum safe crypto. So currently these systems are not secure against quantum. If we have this large 4,000 qubit quantum computer today with us, then we can break this RSA and other ciphers. Okay. So these are not safe, and doubling the key size will not also solve this problem for asymmetric. So we require quantum safe cryptography. Okay. And what are those that we will see? So there is an important Kirchhoff's principle in cryptography. What does it say is that you should not rely on the obscurity of your cipher. So the key idea is that only the secret key or the key which you are using for encryption will be secret. Other things will be available to the attacker, like the encryption algorithm. So it will be public. So when your system will provide maximum security. So what we are saying is that if you see about this DES, so what we are saying is that only this key is secret. Rest how this algorithm works, it is known to everyone. Okay, only the thing which is kept secret is this key. Rest other system details are known to everyone, and we should design such a system that its security depends only on the key, secrecy of the key. So before this Kirchhoff's principle, generally people in the before 1950s or so, what the people do is they keep this design of algorithm also secret. Okay, so they keep this also secret. So by keeping this secret, they think that they are providing two layers of security. First is that what algorithm is used, how it works is also secret. Okay, and then key is also secret. But the problem is that if there are some vulnerabilities or some weakness in this algorithm, then you will not able to know. Okay, and once this algorithm is leaked, you will be in trouble. But if you follow this Kirchhoff's design principle and you keep the key secret, if the system is compromised, then just you need to change the key. So once you change the key, then you will be safe. But if you are keeping this algorithm secret and in the algorithm secrecy you are dependent, then this design is let's suppose this design is leaked, then there is a problem. So the ideal thing is that you should keep this key secret, and you should not believe that this algorithm will be safe. Algorithm will be secret. So the idea is that our system should be such that it depends, its security depend on the secret key only. Okay. So okay, till now we have seen the symmetric key, and there is one time paired and this AES kind of thing. So we have seen that Grover kind of algorithm is straight there. And in case of asymmetric, we have seen that Shor's and its variant can crack the algorithm. So what is the effect of quantum computer and this algorithm? So let's suppose start with this AES 128. Can anyone tell what is the key length? Key length is 128 bit. So what is the key space? 2 to the power 128. Okay, on a classical computer. So it will provide 128 bit security. If we are having quantum computer, then what will be the security? We will be having only 2 to the power 64 keys. If we apply Grover's, okay, so AES is symmetric key and the key space is 2 to the power 128. So if we apply this Grover, then this key space will be 2 to the power 64. So basically, essentially, we are thinking that our key length is since 128, so it is providing security of 128 bit, but it is providing security of only 64 bit. Is it okay? So if we double the key size, then AES 256 is there. So AES 256 will have key space of 2 to the power 256. So if we use this Grover, then it will still provide security of 128 bit. So this 128 is secure because using the Grover quantum, we reduce the space to 2 to the power 128. Now we have to do this thing on classical computer. So classical computer, you cannot do it on a even supercomputer. But we have seen for this RSA, ECC, and other public cipher. So this 1024 bit is the size of the integer factorization problem. So this kind of integer provides security of this many bits. Okay. So if you see, if we are having this classical computers, then they are providing this many bits of security. And if you use Shor's, then these systems are not secure because this factorization and this discrete log problem are polynomial time solvable on quantum computer. So we are in grave situation in case of asymmetric. Symmetric, it's okay. Just double the key size, then you are safe. Or you can use one-time pad also. So symmetric, if you use OTP, then we are secure. If you use double the key size, then okay. But asymmetric, problem. We cannot use these systems. So what we have to do is we have to have different system which are resistant to quantum attacks. We will see. So okay. So what we have seen here is that this quantum computer is having grave threats on public key ciphers or asymmetric. But in symmetric, there is not that much effect. So okay. So what is the effect if we want to see? So let's suppose we are saying that this quantum computer comes, this source is there, then we are in trouble, as we have shown for asymmetric. So do we need to worry now? Because if you see on this online websites, we are using RSA. Okay, we are using ECC also nowadays. So as we have seen that using Shor's on a 4000 quantum bit qubit computer, we can break it. So if we break it today, then there is a problem. So what we are saying is that let's suppose you are using RSA. So do we need to worry now? So there is a scientist called Michael Mosca. So he has given this theorem, which is called Mosca theorem in 2013. What it says is, what is the security shelf life of your information? That is X year. So let's suppose if I have a secret and I want to keep it as a secret for, let's suppose, 10 years. So it's a possibility that something I want to keep secure as a 10-year kind of secret that I don't want to be revealed till 10 years. Okay. So in defense or in this two country state information, this share with them. So this is the kind of scenario there. Maybe 20 years. Some informations are to be kept secret for 10 years, 20 years. So those information are classified for longer duration. But for us, generally, we require some information to be kept secret for some days or some year. But let's suppose this is a scenario where some country want to keep this information secure for 10 years. And if this quantum computer comes in this duration, then how much time it requires to replace those systems which are having threat? So migration is basically replace the current system which are not secure with the safe systems. So migration time is, let's suppose it's 2 years. Okay. So what is X plus Y? So we want to keep the information secure for 10 years. And if there is a threat, then we will require 2 more years to replace that system. So our X plus Y is basically 12 years. And what is the collapse time? Is nothing but the time we will get a large quantum computer which can break these ciphers. So let's suppose this is 6 years. Then we should worry because we want to keep this information secure for 10 years and 2 years time we will require to replace it. So total X plus Y is 12 years and our collapse time is only 6 years. So this 2 plus 10 is very much than the 6 year. So serious worry. Why? Because let's suppose in 6 year time this computer comes and we are using this for next 10 years. We want to keep them secret for 10 years. So if someone intercept this information and keep in repository, when he has a computer in 6 years, then he will be able to decrypt that. Let's suppose we are using RSA 2048, and somebody can tap and store this information encrypted using RSA. But since it does not have RSA key, so he will not be able to decrypt it today. But after 6 years, let's suppose the adversary has this data and this quantum computer in next 6 years, then he can break it after 6 years. And this information's life is for 10 years. So then we will be in trouble. So did you understand this theorem? That if our security self-life and migration time is more than the time which quantum computer will take, then we will be in trouble. Is it okay? Or any doubt is there, then please ask. So if you see in online SBI, they are using this RSA because what they want to do is they want to do the transaction for whatever this bank or this e-commerce website are using. They want that to be secret for that session only, for 1 minute or 2 minutes or 5 minutes. They want to keep the information secure for that duration only. So their shelf life is only some half an hour or some minutes. So in that case, we are not going to get this. So X is our this thing. So and this Y is let's suppose sometime. And this quantum computer is not going. We are not going to have a large quantum computer with us in next 6 years. So then this X plus Y is very less than the 6 year. So there is no threat. But let's suppose two countries want to keep a secret for longer duration, then there is a threat. So what they should do is they should not use this kind of secret systems, encryptions for longer shelf life. So what is happening is that NSA has published this report, and where they say that Kazakhstan kind of countries are intercepting this HTTPS traffic. So whatever this HTTPS traffic that I have shown yesterday, that this whatever secret communication or this online SBI or this e-commerce, so everyone use this HTTPS, and in that they use this RSA 2048 kind of thing. So today they cannot break that encryption, but what they are doing is whatever traffic is encrypted using those cipher, they are just dumping it in large data centers. So this is the real picture, that they are saying that there are large data centers in this country, and they are storing those kind of information. So what they are planning is, once they have a quantum computer after few years, whenever they will have it, they will be able to decrypt it. And if the information, so what they are doing is they are keeping those kind of information stored in their server that is useful, that may be useful for them. So once they have quantum computer, they can decrypt, so that they can use against their adversaries. So this thing is real. So what is the progress in this quantum computing happening? So if you see in 1998, we are having this, so 1994, we are having this Grover's algorithm. Oh, sorry, 1994, 1906, Grover and Shor's. So 1994, we are having this Shor's algorithm. So what the idea was, this Shor's was having a practical application on this RSA kind of system. So after that, development started for realization of quantum computer. And the goal was quantum supremacy, and that was achieved last year by Google. So what we want to see here is, if you see the progress of last 20 years till 2019. So initially we are having a quantum computer with only 2 qubits, then it increased year-wise, and it become in 2019, Rigetti was having a quantum computer with 128-bit qubits. So these are qubits. So to break RSA kind of system, how many qubits we require? Approximately 4,000 qubits. So it's not like that we will not get this kind of computer in future. The progress is tremendous. So before 1998, we are not having a quantum computer, and suddenly it started after this Shor's and Grover's algorithm, and we have reached till 128 qubit in 2019. And last year also, this Google demonstrated quantum supremacy. So what is quantum supremacy? So what this Google does with this their quantum computer is, so Google demonstrated their quantum computer name was Sycamore. So they did some computation, okay, on a quantum computer, and if we want to replicate that same computation on a classical supercomputer, then classical supercomputer was taking thousands of years. And while this thing was done on a Google Sycamore quantum computer with 56 qubits, it is done in some minutes. So on a quantum computer, it was taking minutes, but if you do it in classical supercomputer, then 10,000 years. So what was the idea? That if we are able to do some computation on a quantum computer, which is not replicable on a classical supercomputer, and if we want to replicate them, then it will take thousands of years. So Google demonstrated that using their quantum computer, they did some computation or they did some calculation. If you want to do the same thing on a classical supercomputer, then it was taking thousands of years. So they claim that they have achieved this quantum supremacy. So what we are saying here is that we should not be keep this that today we don't have large quantum computers, so we should be we should not be replacing these systems, because the way progress is happening, this collapse time, basically time to get a quantum computer is decreasing day by day. And now if you see, all big companies and the government agencies are working on developing quantum computers. So see here, different technologies for realization of qubit. So one promising technology is superconducting circuit-based qubit realization, and other is semiconductor-based. So these are the companies which are working. So here also you find that Indian institute like IIT Bombay is also working. So in this you find that TIFR is also working. So significant progress is also being made in India also in realization of qubits. So what is the idea? To develop a quantum computer, you need qubits. So you have to realize those qubits with using these different technologies. So these things are being done in India also. So the progress which we are seeing, so maybe in next 5-10 years we will see large quantum computers. Okay. So this was the thing in October 2019. Google demonstrated this thing. Although what in the Google claim was that Google was saying that they can do something on their quantum computer which cannot be done on IBM's supercomputer. Okay, so it was taking 10,000 years. Google they claimed that, but IBM denied that it will not take 10,000 years. But still, that thing is like a disputed thing. But the thing is that progress is happening in quantum computing, and it is. Excuse me. Sorry for the interruption. So what we are saying here is, so am I audible and my screen is visible?
Yes, sir.
So what I am saying is that this quantum supremacy has been achieved last year, and a few months back also, Chinese also claimed that they have achieved quantum supremacy using different kind of qubit technologies. So this progress is happening. So we cannot be like that our current classical crypto is secure. So as we have seen this Mosca theorem also, because this collapse time is day by day it is reducing. So maybe we are saying that 6 years. So we should replace our this classical crypto system with quantum safe crypto system. Okay. So what is this quantum safe crypto? It should be resist the quantum attacks. Let's suppose if we have a large quantum computer with us, then also our design of crypto should be safe in case of large scale quantum computers are available. So currently, whatever we are using in asymmetric, like RSA and the other system, which are not secure. If we have this large quantum computer, then they are not secure. So what this quantum safe means, if in advent of large quantum computer, we should be secure. Okay. And to be secure, we are having two kinds of system available with us. So one is called post-quantum crypto or quantum resistant, and other is called quantum cryptography. Okay. So what is quantum safe? Can anyone repeat for me? Quantum safe is nothing. We want to be safe or secure in case of large quantum computer. So in case of RSA, which we are not today, because once we have large computer, then RSA will be broken. So we should replace them. So to replace them, we are having two options. One is called PQC or post-quantum cryptography, and one is called quantum cryptography. So what this post-quantum cryptography is, it is nothing but just replace those RSA kind of system with PQC system, and these systems are conventional system only, but they are not based on the problem which can be solved by quantum computer. So underlying problem which cannot be converted into period finding. So these systems are based on hard problems and cannot be solved by quantum computer. So what we are saying is these systems are conventional system only. They will work on this classical computer only, but they will replace this RSA kind of system, and they are based on different hard problems. Like this RSA was based on integer factorization, but these systems are based on different hard problems, and they cannot be solved by quantum computer. So if the quantum computer cannot tackle this hard problem, so they cannot break this kind of post quantum crypto system. So they are nothing but the classical system only. So what the idea is that they will replace this RSA kind of system. Okay, this PQC based system. And other is called quantum cryptography. So this quantum cryptography will work on quantum systems. So they will require quantum hardware and quantum channel, and they will work on qubits. Okay. So this is a different technology. Okay. So this is only classical conventional only, but the underlying problem is different. Okay. So we'll see. So this quantum safe is consist of two things. Okay. So these kind of these systems are called PQC. In quantum cryptography, so I told you two things are there. One is post quantum crypto and other is quantum crypto. So this post quantum is what? It is classical. It works on normal computers, classical computers. Okay, but based on other hard problems which cannot be solved by. So there is, let's suppose, this lattice based kind of system. So what is the idea is the based on shortest vector problem. Okay, and this cannot be solved. Not solved by quantum computer. So whatever large quantum computer you have, you cannot solve this kind of problem efficiently. So these systems are based on other hard problems. So code based and hash based and isogeny based. So these underlying hard problems are not solvable by quantum computer. So if we have this kind of system in place of RSA, then we will be secure. And there's other thing which is called quantum safe cryptography, which consists of two things: quantum random number generator and quantum key distribution. We will see in detail. So just to recap, classically we are having this key distribution challenge in symmetric key cryptography. Okay, so what was the challenge there? These two parties were there, Alice and Bob, and we want to distribute same key k to them. Okay, and they are far. Okay, so what is the challenge is that we can use this OTP. Okay, and OTP, what was the requirement? Just to have this random key k each time to encrypt the messages. But how to distribute that key? Distribution of this. Distribution is the challenge. So if we have OTP, then we are perfectly secure. no quantum attack is possible on OTP, but the OTP we require this large keys. If we use AES 256, then also we are secure. AES 256, but it also requires these keys. So OTP and our AES 256 kind of system are perfectly secure against quantum attacks. But the thing is, we require to distribute this key between these two parties. They are far away. Okay. So how it is handled? So what was the idea is that using the asymmetric key like RSA. So what are the solutions for this key distribution problem? So using RSA, we were sending these keys between A and B. So let's suppose this A want to share a key with B, then what it will do is, it will just, this key is there and it will encrypt using RSA and public key of B. Okay. So what this A will do is, it will choose this K and using RSA and public key of B. Okay. So public key of B it will use and send. Now this Bob has its private key. So it will apply Bob's private key and the RSA function. So using the private key, Bob only can decrypt it and can have this K. So what we are saying is that using the public key cipher such as RSA, we can distribute this kind of keys. So this key distribution can be solved using this RSA kind of cipher. And then what we can do is, then we can use, if we have these two parties with this K, they can use AES 256 or OTP for encryption. So the thing is that this public key are a bit slower. So we generally don't use them for encryption. What we do is, just to distribute this key, we use RSA and other systems. But these systems are not secure, okay, against this Shor's algorithm. So currently we are using this RSA for this key distribution. By this key is encrypted using public key of this Bob, and then Bob can decrypt it. So Bob will, and Alice and Bob will have the key. Trusted couriers means what they do is just courier the key, this K, and send manually to the B. But it is time consuming, and it is time consuming also, and it is a costlier affair. Let's suppose this A and B are very far, maybe in different continents, then it is time consuming. Post quantum cryptography is a solution, because what we are saying is that this these are nothing but this, they are public cipher only. So what this post quantum cryptography, as I told just now, that these are based on different hard problems, lattice code and other problems, and these are not today no quantum attack on them. So these systems are classical systems only, but today there is no quantum attack on them. Okay, so these kind of systems are being developed and used because there is no quantum attack possible on this system. So it is time consuming, it was insecure. But what is the claim is that today we don't have any quantum attack on this kind of cipher. But tomorrow, if someone come up with other algorithm, maybe some new algorithm like Shor's, which does solve this problem of integer factorization, someone can come with other algorithm which can solve this lattice and code-based problems easily on a quantum computer. So what is the claim here is that today we are secure against this post-quantum cryptography kind of thing, but tomorrow may possible that we can come up with new algorithm. So what is the best solution is quantum key distribution, QKD. So what it does is, it solves this problem of key distribution between these two parties, and it can do this rapid generation. And if we have this kind of QKD with us, so using QKD, we can solve this. And this QKD are hack proof. So whatever large quantum computer you have, you don't have any quantum attack against them. QKD kind of system. So they are based on quantum phenomena, and they use this quantum hardware and quantum channel to distribute the key between A and B. Okay. So what we are claiming here is that if we have this kind of system, then they will provide perfect secrecy. Okay. So Why QKD? So just now we have seen this current system are having issues. So we require QKD and it provides perfect secrecy. Okay. So when did it started? So it started way back in 1960. Okay. But that time there was no this quantum algorithm. But this fellow Wisner proposed first quantum key distribution protocol. But that time it was not accepted because of the reviewer were not able to understand its protocol. But later on, 1984, this Bannard and Prasad proposed the first QKD protocol on the work which was based on this Wisner only. So Wisner was doing some work and which was rejected in the publication, but they work on that work only, and then they propose this protocol which is called BB84 based on their name. So first proposal was there in 84, and what was the idea of this key distribution is quantum key distribution is that we send a photon between these two parties on a quantum channel. And whenever we are sending this photon, let's call it a qubit. So whenever we are sending a qubit between these two parties, if adversary in between try to observe or copy it, then this disturbance, it causes disturbance. And this disturbance is observable by both A and B. So what is the idea? In QKD, we send a qubit, which is realized by photon. So basically photon is sent between these two parties, and whenever E is present, its presence will cause disturbance, and that will be observable by A and B. But while in current cryptography, if current communication, if A and B are communicating on a public channel, okay, so if something is going on a fiber cable, okay, then using some technology, you can, whatever traffic is going between this in this fiber optic channel, you can tap it, okay, and this A and B will not able to know about this thing. So if you see a search on this Google and see how to tap this fiber optic communication, then you will see that there are devices. Using those, you can tap entire communication between this A and B, and you can do the post analysis of that. Maybe it is encrypted thing is going on, but you can tap it and store it on classical channel. Okay, and this A and B will not be able to know about this thing. But if we are having this quantum channel and this quantum A and B, in that case, if adversary is present, then you will be able to know, because it will cause the disturbance on those photons. So what are the properties of photon as used for transferring the information? That is polarization or phase. Okay, so we will see how these are used, and it is proven that theoretically it is unconditionally secure because this is based on laws of quantum mechanics. Okay, if you see our current system RSA and other, they are based on hardness of some mathematical problems. So what we are seeing is that this factorization was hard, but it was hard or for classical computer if you don't have efficient algorithm. So this was the scenario that adversary cannot factor large number. So assumption was a mathematical hard problem. But this QKD are based on quantum mechanics laws. Quantum mechanics laws. So this will provide unconditional security. Mathematical hardness can be someday if come with efficient algorithm, then they can be solved easily. But if this is based on quantum mechanical law, then it will be provide unconditionally secure. So what is then this QKD qubit is realized using a photon. So basically a single photon is sent. So photon is sent between A and B, and information, our binary information which we want to transmit between these two parties, we will encode in polarization of a photon or phase of photon. So we will decide which thing we want to use. Okay. So what is the idea? What is this quantum key distribution does? Can anyone tell? What does this Q distribution does? Quantum key distribution.
It distributes qubit over a quantum channel.
Okay.
So if Eve's present is there, then Alice and Bob both can notice the noise in their transmission.
Perfect, Sandeep. Perfect. So what was the idea that underlying it solve this key distribution problem? Okay.
Is it correct, sir?
Yeah, correct. So just add on something to your what you said is that this A and B party require some key for symmetric encryption. Okay, we can distribute this key using quantum key distribution. So there is a quantum channel, okay, and we are sending some photons, okay, and what we are doing is in that we are encoding our information in photons, information like its phase or its polarization. So on this quantum channel, we are sending this photons, and on this information of phase, we are able to have common key between these two. So once we have this common key established, so what we will do using this QKD process, we will send some photons, and in this photon, we are sending information as a phase value, and measuring those phase, we will derive the key. And once we have this key, then with the current system of OTP or AES 256, we can do encryption and there is no quantum threat. So what we are doing here is this, using this QKD, we are trying to solve that key distribution problem. So at the end of this QKD, this both party Alice and Bob will have common key, and that is perfectly random key. So that key they can use for their OTP or this AES 256 kind of thing, or whatever system they choose. So what are the steps or process in this key distribution? So Alice and Bob, so what it will do is, so Alice will send qubits to Bob. Okay, so it is one way thing only. So this channel may be lossy, so some qubits or photon will be lost in between. So let's suppose it is sending this much photon, so this part is received by Bob. So what we are doing is sending photons, these photons are received. Then they will have this, so some part is lost, so whatever the part Bob is having, so effectively Alice will keep that only as a row key. So the first step is only quantum, rest of the steps are classical only. So on the first step, Alice is sending photons to Bob, and then they will discuss something on public channel and will able to derive a secret key between these two. So how these things are done in detail, we will see. So this part is common for both of them. Then they will do some error correction to get a common key, and then they will do some verification, other thing. Finally, they will have only a small portion of key with them. But as we can see that this millions of photon can be sent per second. So we can construct a large key with this QKD also, faster key we can derive. And once we have this kind of secret key, this secret key can be input for one-time paid or AES 256. So AES 256, how much is the key size? 256 bit only. So using those 256 bit, we can encrypt the messages between A and B. Okay. So there are different kinds of QKD. First is called prepare and measure. Okay. So in prepare and measure, what is happening is that qubit or this photon is prepared in some state, and then it is sent to Bob. And other is called entanglement based. So we will see this entanglement based. First, we will cover this prepare and measure kind of thing, and in that case, we will see this BB84 protocol in detail and in the demonstration, and then we will see this entanglement based protocol. So now start with the history of this BB84 protocol. So this BB84 was given by Bennett and Brassard in 84, and this was happened in International Conference on Computer Systems and Signal Processing in 84 in Bangalore. So see the first conference where this QKD protocol was proposed. It was held in Bangalore, and proposal was given by this Brassard and Bennett, and this event was organized by Professor Bhargava in IISc. So this was the paper which was given in 84. See. So before going into detail of that thing, we should understand how this qubits are used for transferring the information. So that we will see. But timing understand this protocol was given in 84, but practical implementation was done in 89, and that too with distance of this Alice and Bob were only this much distance apart, 32 centimeter. In the 32 centimeter, this Alice and Bob were there, and this key was established between them. So okay, so it took time to realize the system. And today this distance is in hundreds of kilometers. Okay, so so you keep this thing in mind that photons are used. Okay. So before going into that thing, first thing is in QKD. QKD, it solves the problem of key distribution. Okay, and this Alice and Bob, what they do is they send photon. Okay, so as yesterday told that qubits can be realized using photon also. So qubits can be realized by subatomic particles like electron, a photon, or proton, or nucleus. So in our this thing QKD, photon is a thing which is used as a qubit. Okay, and let's suppose this photon is having some polarization. So what we are doing is polarization. So this classically what we want to do is we want to deal in 1 and 0. So basically if you want to send 1010 kind of thing to Bob, so you will use this polarization, and this polarization is a property of photon. And what are the possible choices of polarization? If you see, there are 4 choices. Okay, so what is this called? Vertically polarized photon. So polarization of this photon is vertical. It is called horizontal. It is called diagonal. So we call it plus D or call it minus D. Okay, so it is horizontally polarized. It is vertical. It is horizontal. It can be this and this. So what we are saying here is we want to send information. So what is our information which we want to share? We want to share 0 and 1. Okay. Okay. So the thing is that whenever these kind of photons are there, vertical and horizontal, then they can be determined by a horizontal vertical basis. So you kind of think it's a basis. So it is called rectilinear basis. Okay, and this is called basis, diagonal basis. So what we are saying is that if we prepare photon in vertical polarized photon, so we can prepare this kind of photons. Okay, vertically polarized, horizontally polarized. So and this plus 45 and minus 45. Okay, let's call it plus 45 and minus 45. So we can prepare this kind of photons which are having this kind of polarizations. This is vertically polarized, this is horizontally polarized, this is plus 45 polarized, minus 45 polarized. So if we are having a photon which is polarized by either vertical or horizontal, so if we pass it through, so we can prepare in this kind of basis, and if we pass it through this kind of observer, or if we measure in this basis, what is this basis? It is called rectilinear basis, basically horizontal vertical basis. So if you pass this kind of photons to this kind of basis, in this basis if you measure, then whatever you are sending, if you send vertical, then it will identify this as a vertical. Okay. But if you send it in horizontal polarized, then it will determine it uniquely. So whatever you prepare, if you measure in the right basis, so if you prepare it into, you are preparing into this plus basis, you prepared this thing, and you measure into this basis. So you are preparing this basis and measuring in the same basis, then you will get the same thing as a measurement. But if you measure in this if you prepare in this plus basis, vertical and horizontal, and if you measure into this basis, then what will happen? Because you are measuring in wrong basis, so it will give you arbitrary thing. So if you send this thing, so okay. So understand this thing, that you are preparing in some basis. Okay. So let's suppose there are these two bases, plus and cross. Okay. So we are writing it as a basis. Okay. In the plus, if I want to send, then I will send this kind of thing. And this will be our 1. If you prepare in this thing, then this is your 0 and this is your 1. So understand this thing. If I want to, there are two choices of basis. Okay. This is called plus basis, or we call it as a rectilinear basis, and it is called diagonal basis. So just rename it. Okay. So what we are saying here is that if we want to send 0, okay, send 0 in this basis, plus basis, then what we will send? So okay, so let's write, like I want to send 1 0 1 1 1 0. This is the bit string from Alice. Okay, I want to send. Then what will happen? If I choose, so these are the bits Alice want to send. These are the bases. So I'm this thing. I'm preparing the groundwork for that BB84 protocol. So what I'm saying is, let's suppose this Alice want to send this information to Bob. So what this Alice will do is, it will choose this string, then it will choose random basis. Okay. So let's suppose it chooses R, D, R, R, D, R, and again D. Okay. So, okay, basis is chooses. Now, what I'm saying is that Alice want to send this kind of bits, and if it chooses this random basis R, D, R for this kind of bits, then to send one, what this Alice will send in rectilinear basis. So in rectilinear basis, if you go here, for 1 you should send vertically polarized photon. So what you will send? Alice want to send 0 in which basis? D basis. So then it should send plus 45. So this kind of photon plus 45 polarized photon it will send. Okay. Now someone can volunteer for me. Anyone can volunteer? Anyone, please? So I want to be keep you with me, so you are not lost. Anyone,
So
please volunteer?
again, she will send a vertical.
Yeah. So
vertical.
I want to volunteer for me. So what I want to what I explain here is that we are having two bases,
Yes,
plus
sir.
and cross. We are renaming them as a rectilinear or diagonal basis. So we will use plus and cross. Okay.
Yes,
So
sir.
R and D basis we are using, and if we can prepare photon in this 4 state, which I have explained earlier. So we can prepare photon in this vertical, horizontal, plus 45, minus 45. We can prepare it. So now what we are saying is that if you want to send 0 in this plus basis, then you will send horizontal polarized photon. If you want to send 0 in cross basis, then you will send this plus 45 polarized photon.
Yes, sir.
So perfect. So now I want to send 1 bit in R basis. So you will go to the 1 and this R. So what you will send? Vertically polarized photon. Is it okay?
Yes,
Ria?
sir. Yes, sir.
Again, I want to send one in this R basis. So 1 and R, I will go there. So I will send this photon. Now again, I want to send one, but in which basis? D basis. So it will be, we are calling it as a minus 45. So this kind of photon we will send. Again, I want to send one in R basis. So that will be this. Now I want to send 0 in D basis. So what I should see? 0 in D basis. That will be plus 45 polarized photon. Okay. Let's suppose 2 more bits I want to send. 0, 0 in D basis and R basis. Okay. So what should I send? Dear, I want to send 0 in D basis.
So again, 45-degree polarized.
Plus 45, yeah.
Plus 45.
And again, I want to send 0 in R basis.
So horizontally polarized.
Polarized. Perfect. So what we are saying here is that Alice want to send this kind of bit string. So what Alice do is Alice chooses random basis. So randomly he chooses R or D. So there are two choices of basis. So randomly chooses any basis. And what it does is corresponding to this table, he will send this kind of photon to Bob. So this will be sent to Bob on a quantum channel. Okay. Now what will happen at Bob's side? So this is done at Alice side. Now what I'm saying is at Bob's side, Bob will also do the same thing. He will choose arbitrary basis to measure this photons. So let's suppose arbitrary R and D choices are there. So let's suppose it uses R, D, D, R, or D. Okay. So what I'm saying is it also chooses random basis. Okay. So let's suppose randomly Bob chooses this basis RRDDs for this corresponding photons. Okay. So what I told earlier is if you prepare this kind of photons in this kind of bases and if you measure them in correct basis, then you will get the same thing what was sent. So what will happen if we measure in the wrong basis? So see here, there are 8 choices. Okay. So we are having this kind of photons. Okay. Plus and this thing. So if you measure this in plus basis, okay, plus basis. So then what you will get? It is photon, is basis, measurement basis. And what it will get? So what I'm saying is that photon is prepared in these states, horizontally polarized, and we are measuring in plus basis. So what we will get? Plus only. If we are preparing in vertical basis and measuring in this plus basis, then we will get what we will get. We'll get the same thing. So thing is that this thing will pass through this line, and we will get the same thing. Okay. Think at this vertically polarized photon, it will align this with this axis, and it will pass. Okay. Now we are having this kind of plus 45 photon, and if we are measuring in plus basis, then what will happen? This will either go to vertical or horizontal. So this is plus 45. So if it come here, and there is 50% chance that it will go to this vertical or this horizontal. So what will happen? We are having this kind of photon, plus 45 polarized photon, and if we pass it through the wrong basis, that is plus basis, then we can get either this or this with 50% probability. If we are sending this, then same thing happen. So we can get this or this, either of this with 50% probability. Random. Okay. Okay. Now again this same thing. Okay. So this thing and this thing we measure into cross basis. If you are measuring into cross basis, then what will happen? this thing will pass completely. So we will get the same thing. If we pass through this cross again, then we will get the same thing. Okay. Now, if we have this vertically polarized and horizontally polarized, and if we measure into cross basis, then what will happen? Can anyone tell here? Leah, are you there?
Yes, sir.
So what I'm saying is, yeah, I am sending this photon in vertically polarized. So basically, it was prepared in plus basis, but we are measuring in cross basis. Then what will happen?
So we'll get a combination like random probabilities, sorry, 50% probability of getting
That
the
we will get this plus 45 or minus
Yeah.
45. So we can get either this thing or this thing.
Yes,
Okay.
sir.
Same here. So what is the thing is that some cases, see. So see here, if the photon and the basis are, this photon is prepared in which basis? Plus basis. So if you are measuring in plus, then it will get the correct thing. So this case is correct one. Prepared in this horizontal vertical and measure in the same basis. So you will get the same thing. But here is the problem. What is the problem happening here? You are preparing in cross basis but measuring in plus. So you can get arbitrary thing. Either you get vertical or horizontal with 50% probability. Same thing here. You are preparing in this cross basis. So this minus 45 is prepared in cross basis, but you are measuring in plus basis. So you will get either this or this. So basically it is wrong result you will get. Same thing here. If you are preparing in cross basis and measuring in cross, then it's okay. But here the problem. So out of these total 8 cases, we are seeing that whenever this prepared state and corresponding measure basis are same, then you will get the correct thing. But if you measure in wrong basis, then you get arbitrary thing and it will be wrong. So keep this thing in mind. So what I'm saying here is the same thing I'm going to use here. So I'm getting this vertically polarized photon and I'm measuring it in R basis. So if the prepared basis was R and I'm measuring in the same basis, so what I will get? Same thing. If prepared basis and measure basis are same. So this was prepared basis and this is measuring basis. So what the name was it? Prepared measure. Any issue?
No, sir.
Yeah, please. So what I was saying that this whenever these bases are matching, if L is prepared in this R basis and send this photon according to this one it want to send, so it will get this one and it will decode it as a one here because this table was with both of them. So if it measure in plus basis and get this kind of photon, vertical photon, then you will say, okay, I had one. So this table is for available to both of them. So it will also have, Bob will also have one here. Now this basis prepared in D and measuring in R. So what will happen? This is the case. This was prepared in diagonal basis. So see here, this is the thing, and you are measuring in plus basis. So see here, what is the case? Prepared in this diagonal basis, this thing was sent, and I am measuring in the plus basis. So what I can get? I can get either vertical or horizontal. So see this thing, this kind of measurement will give you either plus, either vertical or horizontal. So plus will give you either this or that. So with this same probability, 50% probability. So since these bases are mismatching, so we can get maybe this or other thing. So let's suppose we got this thing. Since bases are not matching, so randomly we can get either vertical or horizontal. So let's suppose we got this thing. Again, here also these bases are not matching. So we are measuring in D basis, but we prepared in R basis. So if we measure in D basis, so randomly we can get this kind of thing. So bases are matching, R and R matching. So what we will get? We will get the same thing, vertically polarized photon here. And if you see this thing, so okay, so let's first do this thing. So the bases are mismatching, so we can get either thing, randomly thing. So let's suppose we got this thing. Bases are mismatching, so we can get anything, either one of thing. Bases are matching, so we will get the same thing which was sent. Bases are mismatching, so we can get rectilinear. So it was rectilinear. So this basis is rectilinear and it was prepared in diagonal basis. So after this rectilinear basis, what we can get? We can get either vertical or horizontal randomly. So these bases are mismatching. So we can get randomly either a plus or either vertical or horizontal. So let's suppose we got vertical. And again, let's suppose, okay, so let's match this basis. Okay, so this bases are matching. So what we will get? The same thing which was sent. Okay. Now what I'm saying is, if this kind of photon is there received by Bob, then this table is with him. So what he can do is, using this table, he can get the bit string corresponding to them. Okay. Okay. So, okay. What is this horizontal photon represent? 0. What is this represent? It represent 1. It represent vertical polarized represent 1. So what I'm doing is, these photons are there. So seeing this table, you can define about what is the bit. Okay. So this represents 0. This represented 1. This represents 0. This represents 1. This represents 0. So what Alice does is, Alice has seen these bits. She chooses some random basis, then prepared the photons accordingly. Then this photon are sent. Bob also chooses random photons, a random basis, and measure them. Okay. Now this thing has happened on quantum thing. So this was quantum channel. This was quantum channel. Now everything will happen is on classical channel. Okay. So in classical channel, what will happen is, Bob will say, I choose this basis. Okay. At this time. So Bob is disclosing its basis. Okay. Now Alice will match its basis. So they share and match basis. Okay. So what now Alice and Bob is doing? They are sharing their basis. So Bob will say, I have used this basis at this time. So Alice will match at his side, her side, and then what they will do is, Alice will say that whenever the bases are matching, they will keep them as a secret key. Other they will discard. Because if they are having the same basis, then they will get the correct thing. Otherwise, they are getting random things. Okay. So see here, when these bases are not mismatching, then they are getting arbitrary things. So if you see here in this table, first position, so bases are matching. Here, if you see, basis is matching. So what they will do is, okay, they will say keep this bit. So this will be kept. Okay. Now again, this position, second position, what will happen? Bases are mismatching. So they will say discard. Discard. Basis mismatching, discard. Basis matching. Here it is R, it is R. So they will say keep this thing. Basis mismatching, discard. Basis mismatching. So whenever bases are matching, they will keep them. So this bit also they will keep. This bit also they will keep. So what we are observing here is that both are using random bases. So what is the probability of that both A and B are having same basis? Measurement? Can anyone tell? There are two choices of basis. Okay. So what is the probability that A and B both have same basis? Anyone, please?
50%.
Perfect.
Yeah.
So out of how many, then let's suppose Alice sent 100 photon, then 50% time their basis will match. And that will be, those will be used for deriving the key. So here the circle thing, which I have told here, those will be their key. Okay. So they can use these bits as a key. It's perfectly okay or not?
Yes, sir.
Since bases are not matching, So they, whatever the Bob intended, Alice will not receive that thing. So see the second case where Alice prepared bit 0 and Bob is also getting 0. But luckily, because their bases are not matching. So if this R basis is there, then it can get this horizontal also, vertical also. Okay. So whenever these bases are not matching, then it can get arbitrary results. So sometime 50% time it will match with the bits, but sometime it will get wrong also. So if you see here, 50-50 chance that it will, although the bases are not matching, but still they are having same bit. But we are not sure now, because this was based on probability. If bases are not matching, see here in these cases, whenever the bases are not matching, they can get either of the thing. And this can represent 1 and this can represent 0. So it was originally 1. So this minus 45 will represent 1. So if you measure it in wrong basis, then you can get either 1 or 0. Okay. So sometimes you are lucky that you are getting the same bit, but sometimes you may not be lucky. So you will get wrong information. So you are not sure. But whenever this basis, prepared basis and measured basis are same, you are getting the same information. So what you do in this protocol is, whenever bases are matching, you will keeping those information for your key. Others you are discarding. Okay. So everybody's understood the protocol, or shall I need to revisit or recap that thing? So what is the thing is that we are having two bases, and in these two bases we can prepare this photon in this kind of polarization and can represent 0 as this vertical, horizontal, and this plus 45 as a 0 information, and 1 for this we can prepare. So there are two bases. So whatever the bit string you require to send, you choose random basis and prepare the photon according to this table and send. And at the receiver side, Bob also chooses random basis. So 50% chance that their basis will match, and whenever the basis matches, they will keep the information for their key, other than discard. Okay. So now what we are saying is, if adversary is present, then what will happen is that we will see how this thing adversary will come to picture. But okay, so this is the thing which they have derived this row key. This key is not the final key. This circled bits are the row key. What they do is they also check the presence of Eve. So if Eve is present, if Eve is not present, then what will happen? They will have these keys exactly same thing. But if Eve is present, then Eve will introduce error. Okay. How this Eve will introduce error, that you will see. So, okay. So, okay, I think we should move to that demo thing. So it will make it more clear. Okay, so everybody can open this thing in their browser. Just go through that. Search this thing, St. Andrews University. Can you search this thing? St. Andrews University, UK, BB84 cryptographic simulation. Okay, let me share this link with you. So I shared the link in chat box. Okay. So everybody can open this link. And here what we are saying is, time being, just I am assuming that there is no adversary and we want to use this protocol. So whatever working I have explained, that will be useful for you. So everybody open this thing. Everybody is able to open that link which I shared in chat box.
Yes, sir.
Perfect. So whatever thing I have told that there will be Alice there and there will be Bob, and they are having this basis, horizontal, vertical, plus 45, minus 45. So there are two choices of basis. Okay. And what we are doing is, in the actual protocol, we use random basis. Okay. But for starting with this working of this thing, I am sharing here this thing. Okay. Okay. So if you see this interface, it is used for simulating BB84 using polarized photon. In the polarized photon, there are two options: horizontal, vertical, and plus 45, minus 45 basis. So these are basically basis. So now I am choosing horizontal, vertical. Okay. At the Bob side also, I choose horizontal, vertical. So what will happen? Let's fire a photon. So Alice wanted to send one using horizontal, vertical. Okay. So if you see horizontal, vertical here, if you want to send one, then you have to send vertically polarized photon. Okay. And since we are saying that Bob is also having the same basis, so what will happen? If Alice sent one, then in the same basis Bob measures, then Bob will also have one. So since the bases are matching, so they can use this bit as a key. Okay. So if I send 100 photos. So since our bases are fixed, okay, and we want to send this random information, so Bob will also have the same thing because their bases are matching.
Not visible, sir. Not visible.
What is not? Sorry.
Sir, the screen, browser screen, sir.
Oh, why it's not visible? I think I have shared my complete screen. So this browser is visible?
No, sir, it's not visible, sir.
Okay, then let's wait a second. What I will do is, I will, rather than sharing my entire screen, I will
So
share
you can
this.
reshare the screen, perhaps.
Yeah, please. Yeah. Yes. Thank you for letting me know this thing.
Yes, sir.
So what I should do is, I should first so what I should do? Where is the option I should get?
So there may be an option of sharing individual screens like the previous PPT, like this web
Yes.
browser. So you should select the web browser.
Just a second. That is the what I do. So what I am doing is, I'm just what I'm doing. I will just log off that meeting, and again, I think, okay, just a second. Change meetings. No. So are you able to see my screen? Are you guys able to see my screen?
No, sir, not yet.
Perfect. So let me rejoin the meeting, and then I will share the thing. But I think I should leave this first. Are you able to see my screen now?
Yes, sir.
Browser also? Browser window also?
Yes, sir.
Yes, sir. It's all clear.
Perfectly.
Yes, sir.
Then
Browser window also, sir.
now,
Yes, sir, visible. Right now, visible.
okay. So I don't know why it happened.
Visible,
So
sir.
I shared that link also on the chat. So that link you can play with yourself after this session. But timing, you understand this thing that there are two bases are available, and if we keep the bases fixed, so if the bases are matching, then Alice and Bob will have the key. Whatever this Alice wanted to send, Bob will also have the same thing, and they can have as a key. But the thing is, if you do this kind of measurement, so what we are doing here is that some bits we are trying to match. So no error because we are having the same basis. So since our bases are fixed, so we are not secure in this kind of scenario. Why? Because if Eve comes in between and if he knows the basis, then she will also able to know this thing. So let's put this Eve into picture. Okay. So we are keeping this basis as a fixed. Okay. So if I do the 100 photon firing, then what will happen? Bob, Eve will come in between, and if she's also using the same basis, so what she can do is she can have the basis horizontal vertical, and she measures, and again she prepare this 0, 1, and this string in horizontal vertical basis and send to Bob. So this kind of meet in the middleman is possible if we are using the fixed basis. So if they are using fixed basis and then compare this first, so not secure because of fixed basis. So okay, so ideally we should use random basis. Okay, is there one more thing before going to that I want to explain? So if I prepare in horizontal vertical and if I measure in plus 45 minus 45, then what will happen? So since bases are not matching, we will simply discard these bits. Okay, this is the protocol thing, that Alice and Bob, if their bases are not matching, then they will simply discard it. Although sometimes there this bit will match. See here, this third entry. This. They both are having 1, although their bases are not matching. Why? Because when you measure in wrong basis, there is 50% chance that you will get the same bit which was intended by Alice. Is it okay? So whenever these bases are not matching, Alice and Bob are not sure that whether Bob received the same thing or not. So 50% chance that she will receive the same, 50% chance that she will not receive the same. Okay. Now, so whenever these bases are not matching, so they will discard this thing. So now let's suppose we choose random basis. So in that case, what will happen? Randomly, Alice and Bob will choose their basis, and 50% chance is there that their basis will match. So let's photon 100 for. So see this first row. Alice wanted to send value 0 in plus 45 minus 45 basis, and Bob also measure in the same basis. So what Bob will get? Bob will also get the same thing. Okay. So for 0, what Alice might have sent in this plus 45 minus 45. So Alice might have sent this plus 45 polarized photon. Okay, because 0 in this plus 45 minus 45. So you have to go to this basis plus 45 minus 45, and 0 will be by plus 45 polarized photon. So when Bob will measure in the same basis, he will also get the same thing. Okay, so that can be used for key. So here, as Ria told that 50% time randomly this basis will match. So okay. So what we are saying is, out of this 100 photons, 15% time on an average the basis will match, and those matching basis bits will be used for key. So see here, what we are doing is, so out of this 100, what we are saying is that 56 time bases were matching. See here this error thing. So what we are saying is that Alice and 100 photon, approximately 46 were in same basis measured by Bob. So those 46 will be used for key. But directly using this 46, what we do is we follow a error detection process. In that, what we do is we randomly match 20 bits out of those 46. So this 46 is our matching basis bits, and out of those 46, what we do is we measure 20 random bits. If those are matching, it means there is no presence of Eve. What we want to make sure is, if Eve is present, then we will have errors in these bits. So ideally, if there is no Eve in this case, so 46 bits were there, and out of those 46, let's suppose we use 20 for error correct detection. So if there is no error, so randomly we matches 20 bits and there is no error. So what we can do is non-shared key bits. So this 20 bits are shared on public thing. So what Alice will tell, my second, third bits are 0, 0. So Bob will also say, my second and third bits are 0, 0. So they will say, okay, matching. Now they will say this fifth and sixth are 1, 0. So in that they will, this thing they will do on public channel. So as I told in the demonstration, now this sending photon and measuring, that will be done on quantum channel. After that, they will do this thing. They will announce their basis on public channel. So announcing basis will not harm anything. But announcing this 20 bits. So this 20 bits will not be secure because this 20 bits we have announced on public channel. So adversary is knowing about those 20 bits. So what we will use? Non-share key bits. So we will discard this 20. So out of this 46, this 20 we will discard. Remaining 26 we will use for our key or for encryption. So what is the idea? This thing is done for error detection. So if there is E was present, then their error will happen in these bits. Okay. So this thing you understood? So since E was not present, ideal situation is there. So if ideal situation is there, there is no E, then they will keep those remaining bits for encryption. So see what happens if E is present. Okay. So you can use this option, stop E or enable E. Okay. So once we enable this thing, Eve, so Alice and Bob is there. In between, Eve comes. Okay. So enable Eve. Okay. Now I sent a single photo. So see what is happening here. Alice prepared one in horizontal vertical basis. So what Alice will send? Can anyone tell which kind of photon Alice will send to send one? Anyone, please? And I need your attention because it's an important thing to detect this kind of errors. So, okay, anyone, please? What kind of photon one Alice will send for one? So you have to come to this basis, horizontal, vertical, and you want to send one. So what you will send? Vertically polarized photon. Perfect. Now, if you measure this vertically polarized photon in a wrong basis, plus 45, minus 45, then what can happen? If you measure in this basis, this vertically polarized photon, so it can collapse to either plus 45 or minus 45. Okay? Because you are measuring in wrong basis, so you can get either this or this on measurement of this vertical photon in this plus 45, minus 45. So suppose I receive this kind of photon, minus 45 photon. Okay. So if Eve is in between and if we measure in wrong basis, and if she received this kind of photon, minus 45 polarized photon, so what Eve will understand that I received one. So Eve will think that Alice has sent one in this basis, but she chooses wrong basis, although it is having same bit. Okay. So now forget about this thing. That first thing you understand that Alice and Eve. So Alice and Eve, if you see, their bases are mismatching, but there is 50% chance that they can get the same bit. Okay. Now what will happen? Now Bob is talking to Eve. So Eve present in plus 45, minus 45, one state. So what this Eve will send to Bob? So Eve will see this plus 45, minus 45 basis. So here Eve will come and she will send this photon, whatever she received when she measured from Alice. So she received this kind of photon, minus 45 photon. So what it will do is, it will send this photon. Okay. Now Bob is choosing the random basis. So what will happen? Bob, let's suppose, is choosing horizontal, vertical. So if E prepared in this basis and Bob is measuring in this basis. So here also the same probability, that 50-50 chance that Bob can measure horizontal or vertical. Suppose Bob measure in horizontal. Then what Bob will think? That okay, I measured this horizontal polarized photon in first place, it means I observed a 0 bit. Okay. Now what is happening is, when this Alice and Bob will discuss their basis, so they will say, okay, I use horizontal, vertical, I use horizontal, vertical. So okay, they will say, okay, keep this bit. because their bases are matching. So forget about this Eve. Now Alice and Bob are sharing their bases and they say, okay, we are having same basis. So what will happen? They will say, okay, keep this bit. But when they do this error detection, so what they will do is Alice may ask Bob, like, okay, what was your bit? So Alice say my bit was 0. But Bob say I my first bit is 0. So although their basis is matching, but their bits are not matching. What it means? It means if error comes, then it means that there is an Eve presence. So previously we have seen if Eve is not present, then if their basis matches, then their bits also matches because they will have the same thing on same basis. Although they are in this case, what is happening? Error is happening because of presence of this Eve. Okay. So this thing will be detectable. So sometimes this thing will be detectable and sometime it will not be detected. So this error is introduced and 25% time this error will be detected. So see, if I fire this kind of 100 photons. So 100 photons, what I am saying is sometime basis matches, sometime not matches. Okay. So out of this 100, sorry, the total photon is, how much photon is there? 101 photon has been sent from Alice to Bob, suppose. And we are saying that out of this 101, 51 times basis matched. So they will keep them as a key bit. Till now they are not aware about this presence of Eve. But when they do this error detection kind of thing, so what they will do is arbitrarily they will match 20 bits. So out of this 20 bits, 5 times their bits are not matching. Okay. And out of this 20 bits, 5 times their bit is not matching. And if we, so it is how much percentage? 5 is after 5 after 20. So it is basically 25%. So 25% time we are getting error. And 25% error means Eve is present. So what is our theoretical thing was there that if you send 100, then 50% time basis will match. And if Eve is present, then 25% time you will have error. So that we have observed here that 25% time error is happening. But out of this 100, 51 is received and 14 error has been occurred. So in entire 51, 14 time error has occurred. So that is around 27% time. So this is the practical thing happened and this is the theoretical estimate. So around 25% time the error should happen. And practically we are receiving that 27% time this error is happening. So if error is around 25% time, then it means Eve is present. So discard the entire thing. Okay. So what we have learned here is whenever Eve is not present, 50% bits are basis matching and they can use as a key. To determine the presence of Eve, you need to check compare few bits. So here we are choosing 20 bits for error detection. If those 20 bits are matching, then Eve is not present. If there is 25% time error approximately, then Eve is present and discard this entire thing. Okay. So this thing you can explore yourself and there is some challenge after this is given. So you can understand, if you understand this protocol correctly, then you will be able to answer those questions. So this thing you can do it yourself after the session. Time being, I should finish the presentation. So where I was. So quickly I will rush through that thing. So this example I have demonstrated you and we were able to derive that thing. So in that example, something I did not tell you that sometimes the photon is not received at all. Photon is lost in between also. So that thing that Bob can tell that at this time I did not receive any photon. So see here. So these things are when photon is not received. Okay. And this public discussion is that they share their basis, and using that basis they will when the basis matches they will say, okay, these bits we will keep. So this is the thing. So there are so as we say that this QKD is perfectly secure and Eve's presence will be determined, because whenever Eve is there, it will introduce error. Okay. But whatever devices we are using to generate this kind of photons, to measure those kind of photons in those particular bases, or horizontal vertical basis, or Z, XZ bases, those are not perfect. So physical device perfection is the challenge. Due to that, some error is introduced. But day by day, we are having perfect devices. So the thing is that it is theoretically secure, but whenever we implement this thing in actual devices, there may be some device error that can make them imperfect. So there are commercially protocols also available. It's not like it's quantum computer. We are seeing that only small scale quantum computer are available. But in case of QKD, there are products available by different companies, and these are the companies name here, and these are the product name. First thing is product name, and second is the protocol used. So there is a famous company called ID Quantic, which has this Clavis 3 devices, and they use cow protocol. So similarly, this BB84. So BB84 is the foundation protocol, and other protocols are kind of variation or kind of other phenomena they use, and they are able to have their own protocol. So if you see here, there is QNU Lab in Bangalore, and they have also their protocol product, QNL X100, and they use this GPS protocol. So there is one variant, other variant of this thing we have seen on media where photon is sent on a fiber channel. But and the limitation of this product is that approximately hundreds of kilometers you can do this thing. If you want to scale beyond 100, then you require satellite-based QKD. So in the satellite-based QKD, what happens is this satellite sends some entangled photons, and using those entangled photons, they establish key between one station, and using the other pair, they establish key between this second station. And what they do is this thing done by entangled photons, pair of photons, and then this satellite announce this K XOR KB. So Ka is established between satellite and this station. KB is established between this station B. Now what this satellite does is, satellite is having both Ka and KB, so it will announce XOR of Ka and KB. So using this Ka and KB, by XORing with their own key, they can have key of other thing. So if at station B Station B was having his own KB that was established between using this satellite and this station B. Now, if it has Ka and KB, then by XORing it, it will have key of A. So whenever this A and B want to communicate, they can use this Ka for encryption. Okay, and similarly, station A also can have KB. So the idea is that using the entangled photon, this kind of systems are implemented, and this station A and B can be far apart, maybe on different continents. So using satellite QKD, we can increase the distance for QKD. Because if you do it on fiber channel, then you can do it for 100 kilometers only. To have 1000 kilometer distance, you will use satellites as QKD. So highest record is 421 kilometers only. So to have this quantum safe cryptography, we should have this quantum cryptography with us, but these things are costlier and they need separate infrastructure. Okay, but these post-quantum candidates are classical one only. They does not require any extra hardware. They can be implemented on classical computers, so they can simply replace RSA kind of thing. So NIST has called a proposal for this PQC kind of candidate. So this thing is going for several years, and now they are finalized with some candidates, public key encryptions and digital signature. So these kind of this red colored are shown here, and they are based on lattice problems. And in lattice we are having these shortest vector problems. So these kind of problems are not solvable by quantum computer. So the system will be secure until and unless we don't have any quantum attacks on lattice problems. So these are the candidates. So if you go to this NIST website, then you can download the code of these systems and you can experiment. So these codes are available publicly. So you can use them for encryption, decryption, and you can try your hands on that. So in your tool chest, so Michael Mosca say that there your x plus y is greater than z, then you are having thread. So you should have what should you should have in your tool chest. So you should have both the things, because this post quantum cryptography are quantum resistant algorithms, classical algorithms only. So they can be easily replaceable. They can easily replace the RSA kind of system. So instead of RSA, we will use this lattice-based crypto or other crypto, PQC crypto. We can replace them. And we should also have, for long-term perfect security, we should have quantum cryptography, because on quantum cryptography kind of thing, you don't have any attack if you have a large quantum computer also. In this PQC, we are claiming today that today there is no attack, but tomorrow may come. But in case of quantum cryptography, tomorrow also we are secure, because these are based on quantum mechanics laws. Okay, and these are based on some other hard problems which are not solvable by quantum computer as of now, but tomorrow we can come up. So we should have combination of both the things, because this thing is quickly we can replace them. These things are a bit costlier, and there are some limitations in this thing. So wherever this perfect security is required or high level security is required, then you should go for quantum cryptography. Otherwise, in general, we should have combination of both the things. So these are the academia and working on this different vertical of quantum. If you see, so there are lots of institutes which are working on these different verticals. So recently, DRDO demonstrated this QRNG. So QRNG is nothing but quantum random number generator, and it can be used in different kind of scenarios noted here. So quantum communication also we require, scientific simulation, lotteries, other experiments we require truly random numbers. So using this kind of quantum random generators, we can have perfect or true true random numbers we can generate. Also, DRDO demonstrated this quantum key distribution using a variant of DPS protocol. So this was done in last year between two facilities of DRDO in Hyderabad, having distance of 15 kilometers or so. So it was demonstrated there. Recently, a few weeks back, at Raman Research Institute in Bangalore, Professor Urbasi Sinha has demonstrated satellite-based QKD kind of thing between two buildings of that institute. Although the distance is not that much, but the thing is that they are able to use satellite-based QKD kind of thing. So using those things, we can increase the distances. Thank you. If any question, then please ask me. Sorry, I overshoot around 15 minutes.
It's okay, sir.
Yeah.
Any queries from the participants?
So if some of you want to pursue career in this quantum field, then it is attractive and it has future. Because also this quantum computing is used in machine learning and other thing domain also, simulation and other thing. So there is lots of scope there in this field. If you are fascinated by this field, then these are the institute where you can do your PhD or higher study. Or also like ISRO, DRDO and other organizations are also there, where practical products are being developed in these domains. So you can join these kind of ISRO, DRDO kind of organization also. So because there are two kinds of opportunities like that, you can get training also there, or you can be recruited as a scientist also there. If you enter there, and then you can work on this kind of thing also there.
Sir, I have one more question. I want to know your views on hybrid quantum clouds.
Yeah. So the thing is that in quantum computer, what happens is certain problems we can do faster, but it's not like every problem is fastly solvable or we get speed up. So what will be there is the scenario will be like that. Quantum computers are costly. Let's suppose if you want to factor kind of things. So these computers are costly. So what will happen in future is that these computers are not, we are not having it on our, like we are having this classical computer, laptop, mobile, we are having on our pocket or our desk. But these quantum computers are a bit costlier, and they require some kind of environment where minus 273 degree Kelvin is the requirement. So those are bulky, and those are put in research lab, on they require lots of space. So what we feel is that in next 5 or 7 years, we are not going to have this kind of system with on our desk. But what we can do is, bigger companies like IBM and other can develop this kind of computer, and they can host them as a on cloud. So what you can do is, you can run, you can buy the time on quantum computer, you can submit your job on that quantum computer and can get your results. So what is the idea? This let's that we have seen on this Qiskit, and also IBM has hosted quantum computers. You can run your circuit on them. So what will the scenario will be there is that these quantum computers are costlier and require space. So we will not be having it on our desk, but this will be available in the, even large computer will be available on cloud, where you can pay and use them. And the second thing is that this quantum computer is not like that it will solve all the problems. Certain problems it can solve faster, but not all problems. So wherever we are getting quantum advantage or speed up, those kind of problem we will run on them on cloud. And second is that uh, other problems we can do fast on classical computers. So whatever, wherever we are getting speed up, only those problems we will run on quantum computer. Other things we can do, and we will be doing on classical computers only. So, and the second thing is that in quantum algorithm development, if it happens, so tomorrow, today we are having only few algorithms. Tomorrow, we can come up with new algorithms that can speed up other thing also. Like we see this searching is speed up by Grovers, this factorization is speed up by Shores. So tomorrow, if we have come up with new algorithms which can speed up other things which are difficult on classical computers, that can be speed up on quantum computer. So in that case, we can run those kind of thing on quantum computers.
So, sir, in last 4 days, I've been so we got very good exposure from like from you for QKit as well as QSKit, and I've also been working with SirQ, Google
Okay.
CIRQ, and so nowadays all of the applications are containerized, right? And they can run on either like Kubernetes cluster or Docker cluster, or we can also run on our supercomputer as well as our clusters in
Yes,
our
yes.
universities, right? So that will help us get more into the like more quantum circuit designs and more people getting
Yeah.
into the
So my
field.
personal view is that, like in
So
India, like in case of classical computer development, if you see, these chips and processors majorly developed in other countries, but India took pride in software
mhm,
development. So what they did is, hardware point of view
yes.
we were lagging, but in software development
Mhm,
we matched with the best in the world. So in today's scenario, what is
yes.
happening is that maybe in IBM and other companies and other countries are moving fast ahead, but this time government is also serious that we should have our own quantum computers and other things. But until and unless you don't have
Mhm,
your own quantum computer, what you can do is you can start quantum programming, quantum algorithms you can start, because these things are available on cloud
mm,
freely by Google and other companies. So what you can do is, by the
mm,
time only few or selected one will be working on development of quantum computer. But what about the other population of the country?
mm,
If they have interest in this quantum computing kind of thing, then they can go for quantum programming, because once this computer will be available, so there will be a huge demand of quantum programming and quantum software developers. So people can move into the direction also.
mhm.
So
Yes,
if
correct.
somebody is saying that, okay, I don't understand much of this quantum mechanics, this entanglement and other thing, I don't understand, then what they can do is, this simple phenomena they should understand. What is quantum parallelism and how we can use it for our advantage. So algorithm development,
Mhm,
implementation kind of thing, people can start working from today also. So for that, they need not to wait for quantum computer to come up.
mhm. One more thing, sir. One more thing I learned from you, sir, about the intellectual property
Yes.
rights, and that's a very key
Yes.
concern, right?
So if you are doing, if you
So
are,
I was
if you are doing some novel research or some secret kind of thing, if you are developing, then you should not develop it on a public platform. That should be inside
of
your
course.
laboratory or some where others don't have access. So you should be doing this thing on your private thing.
So currently in India, is there any institute providing this kind of facility?
Quantum computer or other thing? What you are asking?
Quantum simulator right
So
now. Maybe
yeah,
quantum
so
computer later
if
on
you search this
on a
Professor
cloud.
Urvashi Sinha, they have sent they have developed this kind
Mhm.
of simulator last year. So you search with her name,
Okay.
so you can find that kind of simulator.
Uh-huh.
Okay, and she is also having publication on that thing.
Okay.
Or
Uh-huh.
otherwise, this
All right.
Google
Thank you very much.
QKit that I demonstrated in the previous sessions, let's say a safe kind of thing.
Uh-huh.
You just simply download it and you can run a small circuit on that.
Yes, I did that, and I also got Docker image for from Google about for Circu,
Yeah.
which I can run on my local
Yes.
like local
Yeah.
machines.
So for if you are
All right.
a
So thank you very
beginner,
much for the
if you are
success.
a beginner, then there is no problem running things on IBM and other things. But whenever you want to do some
Mhm.
serious research or something, then you can do it on your private thing, not on public kind of thing.
Mhm. All right, sir.
Yeah.
Thank you very much.
Smita ma'am, I am done with the presentation. If any more question is there, then I am able to, I will willing to take any question. So ma'am, since there is no question, I can stop here. Smita
Okay,
ma'am.
sir.
So I shared my email address yesterday on chat box. So if you have any query or any career guidance or something you require, then you can write me email.
Sure, sir. Thank you very much.
Okay.
Okay, sir. So thank you to took the time out of your busy schedule and provide us information regarding quantum computing, gates, quantum circuits, and last quantum cryptography.
Thank you, ma'am.
Yeah. Asmita ma'am, are you there?
Oh, sorry.
I think, sir, ma'am is not there. Thank you so much, sir.
Okay, thank you.
Okay, thank you, sir.
Okay.